Okay, let's continue looking at kernels, and this will lead to the definition of an ideal. Ring homomorphism and ideals. So what I want you to notice is that kernels of homomorphisms enjoy very strong closure property. They're subrings in particular, so they're closed under addition and multiplication, but they're better than subrings in some sense, so they are more than subrings. So that's the content of this next lemma that I'm going to write down. Let f from R to S be a ring homomorphism. Let's write I for the kernel of f. Then I is a subring of R. That means that it forms a ring in its own right with the operations borrowed from the mother ring R. Furthermore, it enjoys some stronger closure property. If X is in I, any element of I, and A is in R, then AX is in I, and X times A is in I. So what this says is that not just, so saying that I is closed under multiplication means that if you take two things from I and multiply them, then you get a thing in I. But this condition here is saying that something even more is true. You take one thing from I and take whatever from the ring, need not be from I, any other thing from the ring, when you multiply them in either order, the result is still in I. So that's what I mean, that it enjoys a closure property stronger than just being closed under multiplication. So the fact that I is a subring, I mean, all of it is just straightforward verification. So you have to check that I contains 0. Of course, because 0 goes to 0, I contains 0. Then you check that it's closed under addition. And then you have to check this property. Checking this property in particular means that it's closed under multiplication. So the fact that I is closed under addition is just saying if f of A is 0 and f of B is 0, then f of A plus B is 0. Right? If A is in the kernel, B is in the kernel, then A plus B has to be in the kernel. That's true because f is a homomorphism, and f of minus A also has to be 0, and that's also true because f of minus A is minus f of A if f is a homomorphism. So these are true. So this I won't write down. Maybe I'll just write down this extra bit. What happened to my... Okay. So let's just check this extra bit. The main point. And it's also, there's hardly anything to write down. Oops. So proof of the last part. So what do I need? I need to take a thing in X and a thing in I and a thing from the ring in general. So let X in I and A in R. Okay. Then I compute f of A times X. Because f is a homomorphism, this is f of A times f of X. So this is since f is a homomorphism. And now this is equal to f of a times 0, and by 0 I mean 0 of s. And why is this? This is because x is in the kernel of x, right? I is the kernel, see? And being in the kernel means when you apply f to it, it becomes 0. Since x is in I, which is the kernel of f. And now anything times 0 is 0. This we proved when we talked about rings. That element of the ring times 0 is always 0. So that tells me what? That tells me that f of a times x is 0. But that exactly by the definition of kernel, this means that ax is in the kernel. And the other one is exactly similar. Yeah. In that case, you'll just get 0 times something is 0. All right. So this actually leads us to the definition of a ideal. This closure property enjoyed by the kernel is exactly what you want to define an ideal. So here's the definition, the main definition for the first part of this chapter. Let R be a ring. A subring I of R is called a left ideal if, so that's the new word, if A in R and X in I implies A times X is in I. A subring is called a right ideal if A in R in X in I implies X times A is in I. And finally, a subring I of R is called a two-sided ideal if A in R and X in I implies AX in I and XA is in I. Yeah. So we have a notion of a left ideal and a right ideal and a two-sided ideal. And two-sided ideals will sometimes simply be called ideal or simply ideal. Okay. So what we just saw, this lemma up here, this lemma, this condition, this tells you that the lemma says, lemma we just proved says that kernels of ring homomorphism are two-sided ideals. So if you did that exercise of computing the kernels of those homomorphisms, you have some examples of kernels now. Okay. Of course, in a commutative ring, every ideal is two-sided because there is no left or right. So in a commutative ring, every ideal is two-sided. So we just call them ideals. Okay. And zero subring, 0 is always an ideal. Always an ideal. And then the R itself So 0 of R is always an ideal in R, and R is always an ideal of R. So these are, of course, trivial examples. If you have something else, that's called a non-trivial ideal, non-trivial non-zero ideal, and those are the interesting ones. So I'll give you some examples.